I'm Joe Curielli. I want to introduce Nick Mahlstedt. Nick's presentation today is titled Molecular Hydrogen from Sedimentary Organic Matter at High Maturities. Nick's a petroleum system analyst with the Geos4 in Germany and has been there for about 10 years, like a little more. He's currently serving also as a guest scientist at the Organic Geochemistry Group in EAOG-TSOP in Potsdam. His PhD is in Applied Geosciences from the Technical University of Berlin, and his current major interests include petroleum system analysis, sedimentary basins worldwide, generation of oil and gas, compositional kinetic modeling, and of course today's topic, which is generation of hydrogen from organic matter, which is sort of a vast interest right now, just about anywhere in the globe. We're going to take questions in the chat box as we go along, or if you'd like to do them verbally, please hold them till the end, and we'll go over them all when Nick finishes. And with that, Nick, go ahead. It's all yours if you want to share your screen.
All right. So do you see that?
We've got it. Yeah, you're not in slide mode, but we can see. Yeah, now you're in slide mode. Looks good.
Okay. All right. So yes, as you said, thank you for having me here today. Going to talk about today molecular hydrogen from sedimentary organic matter at high maturities. Especially, I will report about 2 papers we published in 2022, because here we covered all the, let's say, important or classical different organic matter types, like lacustrine source rocks. Those were provided from our Chinese colleagues from the SK2 well in the Songliao Basin, the Shuangbiaohan here and Chengshanwang. And for the type 3 coals and marine shales were provided by Christopher Boreham from Geoscience Australia. Yeah, for both papers, the similar people took part in the investigations, mainly Philip Weniger from BGR Hannover, who did excellent work on the open pyrolysis TCD to analyze the hydrogen generation, and David Misch and his team from University in Leoben in Austria. They provided the BIP scanning electron microscopic data of the samples. And at GFZ at that time, under the supervision of Mareike Noor, the FTIC-RMS high mass spec resolution results were generated. Okay, so what was our motivation to dive into this topic of hydrogen generation? Mainly political reason, of course, in this today's climate and of the energy and the Green Deal. So the clean energy transition actually is not only about lowering gas or carbon emissions, but it's also about securing or guaranteeing secure and stable energy supply. Nevertheless, the production of and use of energy account for more than 75% of Europe's greenhouse gas emission, and therefore decarbonization is really critical to reach Europe's climate goals and carbon neutrality, in part by developing cleaner sources of energy. And those energy sources are mainly natural gas, still, especially hydrocarbons, but first of all, also hydrogen, which is important as it's the most energy-rich gas and a truly clean energy carrier because it's devoid of carbon, of course. Nevertheless, hydrogen accounts for less than 2% of Europe's present energy consumption only, whereas 96% of this is gray hydrogen. So gray hydrogen is formed from steam reforming using hydrocarbon gas and hot water, and thereby freeing large amounts of carbon dioxide, and which causing a big environmental impact, of course, at admittedly relative low economic cost. So as blue hydrogen, which is basically gray hydrogen, but with carbon capture and storage technology, has a similarly bad carbon impact at higher costs, Europe's strategies focus mainly on green hydrogen, which is produced by renewable powered electrolyzers, but presently most expensive option. Now, geological hydrogen could offer a very clean and low-cost solution, and is actually the only energy positive hydrogen source delivering 11 times more energy than is needed during its production. So it's attractive. In contrast to Australia, the geologic hydrogen is not yet part of the clean energy strategies, mainly because the resource potential is unquantified. So in any case, natural hydrogen is quite ubiquitous over the world and appears in high relative amounts and many places in a lot of geological settings. It appears as free gas in coal basins or hydrocarbons fields in ore bodies above fault zones and in soils, and as gas in gas inclusions and as dissolved gas in aquifers and waters from hydrocarbon fields. Now, the sources for this geological hydrogen there are as many as there are places where you can find it, with some having potentially high resource potentials, other don't. So there are numerous abiogenic sources with serpentinitization or hydrothermal vents or radiolysis of water being considered the most important geological process, leading sometimes to really high prolific hydrogen seepage. For instance, in Mali, there's almost pure hydrogen produced from one well over the last 10 years. Now, in our 2022 papers, we could show that there might be an additional biogenic hydrogen potential from the thermogenic cracking of overmature organic matter during aromatization and condensation reactions, which might be unlocked using established drilling methodologies, which nevertheless have, of course, to be further developed and refined. So our main approach or goals and themes of the 22 papers were not only to assess a global hydrogen potential coming from the huge number of organic matter finally dispersed in all the sedimentary basins in the world, but also to assess the potential in individual basins based on or related to the richness of the organic matter and the thermal ability of the most important source rocks in those basins. This is mainly what I will talk about today. Today, because it's a topic. I will also touch upon a little bit on the preservation topic of hydrogen and do a little bit of ground truthing, meaning I try to discuss if this potentially generated hydrogen is actually found in the deep subsurface or not, and what might be the reason where this has vanished to. Okay, so the main approach in our investigations was to use open system pyrolysis thermal conductivity detection run by Philip Weniger at BGR to investigate the evolution of hydrogen and other low molecular weight compounds. The key element actually is to use natural maturation series covering the three main kerogen types. So we used as humic coal type 3 samples. We used samples from the Permian Pachawara coal from the Cooper Basin in Australia. For as type 2 marine organic matter, we used Arthur Creek, Middle Cambrian Arthur Creek Formation shales from the Georgina Basin and some others coming from US and European basins. And as lacustrine organic matter, the Shahezi, the Cretaceous Shahezi, shades from the Cretaceous Shahezi Formation in the Songliao Basin in China were provided. So it is really important to look into natural maturity series because we need the yields or the evolution of gases from samples from all levels of maturity to verify or calibrate the findings or the kinetic models we built for the hydrogen and methane generation using levels, samples of lowest level of maturity. So because during especially open pyrolysis, not all the chemical reactions taking place under natural conditions can be truly simulated. All right, so let's start with the elemental composition as shown here in the Van Crevelen diagram, and how the compositions of the different organic matter types evolve with maturity. So for all kerogen types, first during diagenesis up to 0.5% vitrinite reflectance, we see a decrease in the oxygen over carbon ratio, mainly by the release of the most labile functional groups, oxygen-containing functional groups. Then during catagenesis, up to 2% vitrinite reflectance, the hydrogen over carbon ratio decreases to roughly 0.6%, not percent, but 0.6. And by the cracking of the least stable bonds to more stable bonds, and generating petroleum, aliphatic petroleum for type 1 kerogen, and more aromatic petroleum perhaps for type 2 to 3 source rocks. Then in the metagenesis zone now, above 2% vitrinite reflectance, all the kerogen types have a pretty similar composition on an similar elemental composition, and that is exactly the place where we expect our late methane and late hydrogen generation to take place. Not by normal cracking, but for late methane, we have a final demethylation of pretty aromatic organic matter, and with further ring growth and additional condensation of the aromatic nucleus to higher aromatic nucleus, or to bigger structures, we see the release of free hydrogen. Yes, so this is pretty nicely in line with results coming from ultra high resolution mass spectrometry for rock bitumens, or more specifically of a maturity parameter formulated by Noah et al. Using the changing ratio of certain areas in the DBE over carbon number plot. So representing the aromaticity or the size of the aromatic core structures over aliphaticity, or the level of alkylation of those aromatic core structures. So we see here the maturity parameter evolves through catagenesis up to 2% vitrinite reflectance, roughly 550 to 600 degree Tmax values. It nicely increases just due to the cracking of the side chains and to the concentration of more aromatic organic matter. Then we see an inversion, and the maturity parameter actually collapses during metagenesis due to extensive polycondensation reactions leading to pyrobitume or insolubilization, and with that to late gas generation, methane and hydrogen. A similar inversion and at similar maturities can be also seen for organic matter and shales by increasing spin densities representing stabilized radicals in the course of cracking, and loss of those stabilized radicals in the course of condensation leading to pairing of those radicals. Now let's have a look into the open system pyrolysis data, and for methane here on the top row, and for hydrogen in the bottom row for the three organic different natural maturity series, humic type 3 coals on the left, in the middle marine type 2 shales, on the right hand side lacustrine shales from the Shahezi formation. So under lab conditions, methane and hydrogen is really generated over extremely broad temperature intervals, whereas methane seems to be generation of methane seems to be finished at lower temperatures, roughly below 900 or earlier, below 900 degree C. We also see that for methane, the generation rate curves are more or less nicely monomodal, have a nice monomodal shape, and yields decrease with increasing maturity. So that's indicating that during maturation, the precursor structures for methane in the kerogen are destroyed, or gases was generated. For hydrogen, in contrast, pyrolysis seems to be still going on at highest pyrolysis temperatures of 1100 degree. And the evolution pattern is much more complex, at least for the less organic lean shales, marine and lacustrine shales. So this is an indication that hydrogen generation is associated with both with organic matter and inorganic matter decomposition, and with equilibrium reactions between the generated pyrolysis gases like methane, water, or nitrogen, carbon dioxide, and carbon monoxide. So evolution patterns like that can really not be nicely used for determining the kinetic parameters for hydrogen generation from organic matter. So for that, we had to use the more organic-rich Pachavara Formation coals and one Coley shale sample from the lacustrine Shahesi Formation. But let's first have a look into the important information that can be directly derived from the evolution of the cumulative pyrolysis yields. So on top, we see that cumulative methane yields correlate very nicely, or plus minus, with TOC and with the hydrogen index. So the methane potential is linked with live carbon, or with the label kerogen fraction that is assessed as S2, as the S2 parameter during rocky valve pyrolysis, for instance. And in contrast, the cumulative hydrogen yields correlate very nicely with TOC, but not at all with the hydrogen index. So that tells us that the potential is rather linked to dead carbon, or carbon itself. So the main message we can already take from here is that the best hydrocarbon sources are not necessarily the best hydrogen sources. And that total organic carbon, not hydrogen, better predicts hydrogen HI, better predicts hydrogen generation potential. Okay, let's go a step further. So we wanted, with the data, to define the base of the methane window, and that here on this side are shown the open system pyrolysis DCD yields for methane, and here the potential decreases from roughly 40 milligram per gram TOC at immature stages, and most importantly phase out at roughly 650 degree Tmax, which is roughly equivalent to vitronitroflectance of 3.5%. So, and that is for all three maturity rates. Now, the closed system MSSV assessed late methane generation potential, which refers to an additional late dry gas methane charge, which goes almost completely unnoticed on an open system condition, probably because concomitantly formed hydrogen radicals don't have the chance to interact with the carbon to form this methane gases under the open system condition, because they do not remain in the closed system. So here we see that late gas potentials also increase through catagenesis up to 550 degree Tmax, which is refers to roughly 2% vitronitroflectance, or the beginning of the metagenesis. And then the potentials decrease and phase out at the same maturity level of roughly 3.5% vitronitroflectance. So in both systems, we see a similar phase out of methane. Now, the free hydrogen window was also can also be constructed or assessed And we see also a similar evolution with an increase in potential and then during catagenesis, and then a decrease in potential during metagenesis. So that is mimicking really the evolution of the late methane potential. And then at roughly 650 degree Tmax, referring to 3.5% vitrinite reflectance, there's still 20 milligram per gram TOC hydrogen potential left, which we can view as a free hydrogen generation potential because no further methane is generated at those maturities. So the phase out of this potential can be assessed, very roughly estimated to occur at roughly, I don't know, 720 degree Tmax, which would be equivalent to a RO of 5%. Okay, so taking this number, we try to do an assessment of a global hydrogen in place, as you wanted to estimate a number by revisiting back of an envelope calculations done 10 years before for assessing global shale gas in place and for estimating the released number by the Energy Information Administration in 2050. So the back of an envelope calculation were based on 5 generalized assumptions. The first one, planet Earth contains roughly 2 × 10 to the power of 16 tons of dispersed organic carbon, of which 30% are overmature and have a hydrogen gas potential of 0.1 gram per gram TOC. And then, fourth assumption, only 10% of this carbon resides in organic rich source rocks with TOC contents greater than 2%, and only 1% of those source rocks, so carbon, is in a prospective area for development. Okay, our found number was very close to that given by the EIA. So that tells us that the generalized assumption were roughly correct. Now, doing the same for the global hydrogen in place, using very similar assumptions, we find that the resource potential is only 1 order of magnitude lower than the global in place shale gas potential. So this number is 1 order lower than this number. So the assumptions were pretty similar. So the same number of dispersed organic carbon, but the organic carbon had to be a little bit more mature. And the measured hydrogen potential was 20 milligram per gram TOC, or the factor of 0.02. And we assumed that 10% only remains in place and is not expelled or reacted to form other products. All right, now going into more applied assessment of hydrogen in place, we could do the same calculations, assuming the same assumptions for individual basins here, for the Songliao Basin, the Cooper Basin, and other European basins, and came up with a number that is in the same order of magnitude the natural gas concentration in the Barnett Shale. So interestingly, for coals, the potential is really highest, which is or higher than those shale gas potential, just related to the organic richness of coals, of course. So that might be the best source rocks for hydrogen generation. Okay, so now to kinetics topic. So the stability of the different bonds within organic matter can be described by kinetic parameters, usually an activation energy distribution and a single frequency factor. Using a single frequency factor means that low activation energy indicate weak bonds that are stripped away or are generated upon early maturation, and high activation energies indicate strong bonds that are realized during late maturation. So at least 3 recorded generation rates or three heating rates serve as input parameter to define the starting value of the frequency factor A, and using nonlinear, or by solving this famous Kissinger equation, and by using further nonlinear regression methods, we can optimize the model to fit the measured heating rate, generation rate curves, to reach a final value of the frequency factor and an energy distribution. So now we have all the parameters in place, and just by changing the heating rate to geological heating rates, we can predict the timing in geological times. So here are the heating rates shown for methane and hydrogen for the Pachavara formation sample exhibiting maturity of roughly 0.75%. We see here that at all heating rates, the gases are generated over this very broad temperature interval, which translate to very broad activation energies. For hydrogen, we even had to use a 2 kilocalorie per mole spacing to cover the complete bulk reaction within 25 activation energies, which is a prerequisite in the Kinetics 15 software to calculate those activation energy distributions. So the very same is true for the Shahese formation sample, which is a little bit more mature and exhibits vitronite reflectance around 1.3%. So now extrapolation of the generation to geological heating rates shows that methane here in pink is always generated earlier than the hydrogen. And for both gases, both gases are generated earlier from the less mature sample. So the less stable precursor structures still present in the less mature sample are already generated or stripped away during maturation in the more mature sample. So the curves are shifted to the right to higher temperatures. Generally, those broad activation energy distributions really imply that there are many different precursor structures or different bond types, and also perhaps different reaction mechanism leading to the formation of those gases, which is quite in contrast to late methane generation under closed system pyrolysis condition, which I assessed during my PhD thesis. So late methane generation can be described by a single activation energy at very low frequency factor, and is descriptive actually of a specific formation mechanisms, namely the previously discussed final demethylation of aromatic nuclei involving condensation reactions. So extrapolation to the geological heating rate really shows that the generation of this late methane is much narrower and proceeds in metagenesis at temperatures above 200 or between 200 and 250 degrees. Now, one important information is here that late methane and also the bulk methane curves from open system pyrolysis cross at roughly 90% transformation ratio here, which marks the end of methane generation. And 250 degree, taking vitronite reflectance values, is corresponds to roughly 3.5% vitronite reflectance. So this confirms that our kinetics are pretty correct, as the natural maturity series also shows a phase out at the same for the same temperatures or vitronite maturation levels of 3.5% vitronite reflectance. Okay, now what about the kinetics of free hydrogen generation? because the hydrogen radicals are really reactive with hydrocarbon gases, free molecular hydrogen is not likely to be formed prior to the end of methane generation under natural conditions. So we try to construct a geologically more realistic hydrogen generation scenario by using certain adjustment factors shown here. So by plotting, for example, the transformation ratio evolution of hydrogen and versus that of methane for all three rates we used as input parameters, the generation shows a very similar evolution with temperature. So in the first temperature zone, which is the main stage of methane generation, and here hydrogen generation is just beginning. So we multiplied here the hydrogen yields with 0. In the second temperature zone, hydrogen generation accelerates a little bit, and methane generation becomes slower. In this zone, adjustment factors increase from 0 to 1. In the third zone, methane generation dies off, and we have the main stage of hydrogen generation. And here we multiply the hydrogen yields by 1, increasing to 1.6 at the Tmax value, and then decreasing again to 1.0. In the fourth temperature zone 4, we have no methane generation at all, and only hydrogen is generated, so we can multiply by 1. So doing this for all three transformation ratio rate curves, we really get rid of a substantial proportion of the early formed hydrogen here in yellow, and get new curves, which are used as input parameters to calculate the hydrogen kinetic models, which we call factor mix models. Okay, they are shown here in blue, in light blue for the Pachavara formation and the Shahese formation sample. And what can be nicely seen is that for both samples, the activation energy distribution looks very similar with low frequency factors, and at extrapolation to geological heating rates, they are almost identical. So that is very good, important. So we found that for very similar kinetic parameters for different types of samples at different maturities. So we think that our kinetic predictions or parameters are sound and could be used using normal basin modeling software. Okay, here are again the kinetics shown for the different energy gases which we can expect. At lowest temperatures, we see oil and gas generation from kerogen cracking, which basically depend on the organophases, so the distinct temperatures. For secondary gas cracking, temperatures for gas cracking for in-source and in-reservoir cracking can be also variable, depending a little bit on the waxiness of the oil phase. Now, hydrogen generation now begins in the metagenesis zone above 200 degrees and 2% vitrinite reflectance alongside late methane generation. When methane generation has come to an end at 250 degrees or 3.5% vitrinite reflectance, on roughly 40% of the hydrogen potential is generated, leaving 60% to be generated between 3.5% vitrinite reflectance and 5% vitrinite reflectance, or 250 and 400 degrees. So the kinetics really seem to be invariable for those late gas generation curves, because which makes sense because the dominating reaction mechanism is polycondensation and ring growth within the spent organic matter. So now we applied those kinetics in different geological settings, and trying to begin with this, and we saw that maximum hydrogen generation rates were in the range 1 × 10⁻⁻8 milligrams per gram sediment per year, which is right in the range of utilization rates from the biosphere under survival conditions. So meaning that there could be a steady state coupling of the biosphere with the geosphere. So feeding the deep biosphere by geological reactions. Nevertheless, the high generation temperatures for hydrogen above 200 degrees actually, of course, fully precludes that in situ utilization by the deep biosphere, and because above 80 degrees, more or less everything is pasteurized. But it is thinkable that the generated hydrogen migrates along folds or via unconformities into shallow horizons where it could be degraded by the deep biosphere. We also applied the kinetic models, the methane and hydrogen kinetic models of the Pechavara Formation source rock sample to a published 3D basin model of the Cooper Basin in Australia. So the burial history of the most mature Burley 2 well in the depot center here really shows that hydrogen is starts to be generated above 200 degrees, and at highest paleo temperatures around 250 degrees, roughly 50% of the hydrogen generation potential is realized. At this point, methane here in red is already completely generated. So these maps show the generation of methane on the left-hand side and the generation of organic hydrogen on the right-hand side. And we see nicely for methane that sweet spots occur, that sweet spots for methane here in blue, in the bluish colors, align very nicely with the gas fields in the Pechavara and Alunga troughs, whereas sweet spots for hydrogen on the right-hand side are only very confined, appear only in a very confined area of highest maturities in the depot center of the Napa Murray Trough. So now let's come to a little bit of ground truthing, because actually those explorational drilling and like organic matter hosted pores occur and are indicative of high methane production rates and storage capacity for methane. Now the shielding of those nanoporous pyrobitume by rigid grains in shales might be very important to let those pores survive in the metagenesis zone, which is in contrast to coal coals, to more organic rich coals, where the secondary porosity rather evolves as smaller meso and micropores, and just yielding sorptive storage site for the hydrogen, in contrast to the kind of a true gas phase in the bigger pores of the pyrobitume. So our BIPSEM results from our papers really confirms those literature observations, in that the high mature terrigenous organic matter or samples from the Pechavara Formation and the coaly shales from the Shahezi Formation really did not show any SEM visible porosity. In contrast, the marine Arthur Creek Formation shales Here, the SEM visible porosity increases from 0.1 to 2.5%, going from 1.3 to 3.7% vitrinite reflectance, whereas the organic matter hosted porosity really increases from nothing to around 50%. So the presence of those sponge-like organic matter hosted pores might be very important for the marine shales and for storing the hydrogen in there, because the microporosity found in the coaly organic matter is not as big as in the coal. So the microporosity is rather low in marine shales compared to coals. So this microporosity might prove critical in explaining whether cloaked, or might be critical in explaining the cloaked presence of this hydrogen in the subsurface. So Stainforth and Reinders, for example, they modeled primary migration of oil and gas by active diffusion through kerogen through the kerogen network. And in the same context, hydrogen can diffuse through polymers under high pressures at rates governed by Fick's law. To account for unexpected and sustained shale gas production over time, Mango as well thought that methane and carbon in kerogen are at equilibrium in the source rock, meaning that methane could dissolve conceptually in higher molecular weight organics. So that same might apply also to hydrogen, so that we don't see it anymore in the subsurface easily. Okay, I would like to finish with and wrap up with some metagenetic reactions that involve hydrogen radicals. So during early metagenesis, between 2 and 3.5% vitrinite reflectance, we see mainly late gas methane generation by the recombination of hydrogen formed by aromatic ring growth and methyl radicals formed from the alpha cleavage of kerogen. Then at higher maturities above or exceeding 3.5% vitrinite reflectance, times where no methane generation takes place anymore and the methyl radicals are absent, primary hydrogen is formed by radicals reacting, by the hydrogen radicals reacting with each other. But what also could happen is that secondary hydrogen is formed by reaction of a hydrogen radical with previously present methane. This would leave behind isotopically light methyl radicals, which could again recombine to give ethane, so generate wet gas. This might be important, might be very important mechanism that could explain isotope reversals, or the rollover of the stable carbon isotope of ethane seen in many shales, which nevertheless are not always present. So those rollovers are seen at roughly at 2% vitrinite reflectance going into the metagenesis zone after the normal evolution to heavier isotopic composition with maturity up to here, and then the evolution to lighter compositions in the metagenesis zone. So now here there are many possible explanations for this reversal, and I really cannot go through all of them, but just saying that hydrogen radical reaction with methane to form ethane, isotopically light ethane, would be a nice explanation that falls directly along some lines of some publication that feature, for example, regeneration of ethane via reversible free radical reactions catalyzed by minerals or perhaps also by metals. So that is only as an idea what those late radical reaction might lead to. So, okay, then let's conclude. The generation part is that kinetics and natural maturity series reveal that molecular hydrogen is generated after hydrocarbon generation is over, so in excess of this 3.5% vitrinitroflanes. The kinetics are more or less, we think, more or less established, but further organophases should be tested. For example, I could think of sulfur-rich organophases, which always prove to be a little bit tricky, and yeah, we should do more there. And generation appears to be organic matter type independent, whereas the net building of potential is from concentration and neoformation of polyaromatic ring systems. So we see this here. And hydrogen yield per unit rock volume closely resembles that of economic shale gas. And there's a substantial resource potential in overmature strata in basins where you find mature organic matter, like in the Lower Saxony Basin and the Cooper Basin, on the West Netherland Basin, for example. Now to the preservation topic, secondary porosity for hydrogen storage is present in the metagenesis zone, visible in shales and as microporosity in coals. So the ground truthing confirms that there's really not much hydrogen floating around, but it might hide dissolved in kerogen or just simply overlooked during production and perhaps also reacted, extending the hydrocarbons floor. All right, that was it.
All right, excellent. Thank you, Nick. Let me ask, can everybody hear me? We had a glitch about halfway through here. I just want to make sure everybody's back on audio. Can you hear me okay, Nick?
I can hear you, yes. But
okay.
a few people can't, I guess.
Okay.
Or that are gone, or didn't come back.
Okay, all right. Well, like I said, I'm not sure exactly what happened here, but I was able to log on after we lost it at about 45 minutes. I was able to log on pretty quickly right after that. When I logged on, for some reason, it didn't give me a chat function on Teams, but it moved that to a separate tab in the browser. So I do have one chat question that was put up before the glitch. There may have been some after that we lost, but let's start with a question that I have. This is from Maria. The question is, in your selection of coal, did you go for hydrogen-rich samples like liptonite-rich? In other words, what was the maceral composition of the original coal used in the experiments?
It was, we can take that from the hydrogen versus Tmax plot. So we saw the blue coal samples. They were from Pachavara formation, Permian coals, and they are not overly elliptinitic. So it's just, you see here the maximum HI is around 200 or 300. I think those dots here, they are not really, at higher hydrogen index, they are not really indicative of the, I'm not even sure if that is really the Pachavara formation coal samples or if that is a miscoloration here. So it was just normal humic type 3 coals. I mean, I think if, yeah, that's it.
Okay.
The vitrinate-rich coals.
Okay. Thanks, Nick. As I mentioned, I may have lost others in the chat. If anybody has a question that was in the chat, go ahead and unmute and just ask it.
Hey, Nicolaj, this is Darius. Can you hear?
Hi.
Excellent, really excellent talk going throughout the subject. Yeah, I want to kind of support your observation about this hiding or quenched hydrogen that is obviously there. We know it from pyrolysis experiments. hydrous or non-hydrous. For example, there is thousands of wells in Marcellus shale, which is highly over mature oil going all the way to 4% vitrinite reflectance. However, in those, for sure, if there was any hydrogen, might have been overlooked. But we are even involved in logging of some of those wells with a certain mass spectrometer that can see hydrogen, and we never see anything. So can you comment on that? Because that would be the ideal place to see it, accordingly.
Yeah, not really. Otherwise, that the concentrations perhaps are just not big enough in those low TOC. No, it's not low TOC setting, but perhaps the concentration is not big enough so that really are desorbed perhaps from the micro porosity during this mud logging, or not as quick. I don't know how long those measurements perhaps pertain in time.
Yeah, I mean, if it's not found even in the produced gas, I mean, it's not observed as a free gas. So I concur to your hypothesis that if it's there in those amounts sufficient to be absorbed in kerogen or micropore secondary porosity, but not sufficient to be seen in free gas or produced gas.
Yeah, I think that's obviously the case. So I mean, it's really hard because using pyrolysis you can just approximate how much can be generated. So those hydrogen radicals under open pyrolysis conditions, they probably have no time to really also to react with other compounds. They pair up to form free hydrogen and are there, but under natural conditions, perhaps this hydrogen is also just diffusing away too fast and reacting with other compounds really quick. So it might be not in those high amounts that we assessed.
Yeah, just a final comment. Maybe what I did with Maria a long time ago during my studies on desorption experiments, including crushing, with a ball mill, even the tiniest pores. I don't think we have looked at hydrogen at high maturity coals or shales, but maybe something that could be done to see at the residual gas composition, if it's really hiding in there in the secondary porosity. Something to study maybe by Maria. Okay, I'll let everybody else ask questions.
May I chip in here on the same question, Joe?
Yeah. Mm-hmm.
Because indeed all the potential mechanisms why we don't see the hydrogen that we expect. What about mobility? Is that not greatly or vastly different than for the other gas species? And we know in reservoirs that seals can be, for example, sealing to ethane plus, but not to methane. That methane more easily diffuses out. And of course, hydrogen is so much more smaller than the other species. It's not simply quickly escaping the whole system.
Yeah. So at least in our resource potential calculation, we assumed that 10% max stays retained of this generated methane, hydrogen is retained in the source rock, or that at least 90% is reacted or moved away because it's so mobile. But perhaps that number is still too high and we should assume 1%. That could be, but that would probably just bring it down one order of magnitude. Yeah.
And thanks, Nick. Wonderful presentation as well.
Thanks.
One question for you, Nick. I noticed in the kinetics portion of the presentation that your frequency factors, the A number, are pretty low.
Yes, very low.
7, 8, something like that. Is that? Do you think that's real and has to do with reactivity, or is that simply a sort of a result of the compensation effect with these relatively high activation energies?
No, I think, real or not real, it's really hard to say. I mean, the activation energies, like you see here, it's not very high. It's like 55, but the frequency factor is to the power of 8. so pretty low or high. I think it is realistic. Perhaps in a physical sense, it's really hard to say that most of the times those frequency factors show a 14 or 13 in this at this range, but which is always said to be physically relevant for primary cracking of kerogen. But I think that these low activation frequency factors always seen for reactions where condensation of aromatic nuclei are the reaction, the dominant reaction mechanism to form the detected gas species. So I saw that in my methane, in my late methane potentials. That was to the power of 9. The frequency factor here, it is to the power of 8, and it's kind of a compensation effect, but it's always seen for condensation dominated reactions, I believe.
Okay.
And it makes, I mean, that is why it is really important that to use those natural maturity series, because for this low frequency factor, and we had this generation of late methane, which really is finished at 250 degrees, which really is equivalent to roughly 3.5% vitronitroflex. And we saw the very same phase out at for the natural maturity series at 3.5% vitronitroflex. So that alone tells us that the predictions using those kinetic parameters are at least solid. If they are physically really relevant for the reaction, is written on another paper, but I think those parameters can be used to model can be used as simple parameters in Bayesian models, Bayesian modeling software to model those generation of those compounds.
Okay, great, thanks. Other questions? Go ahead and unmute and ask. Anyone? Okay, then with that, I'd like to close our session today. I'd like to thank Nick Mahlstedt for his presentation, very nice presentation, and also all of those of you who participated, who asked questions, etc. We're going to continue this series between EAOG and TSOP. The next one is, I think, going to be probably another 3 or 4 months down the road. If anybody is interested in making a presentation on their current work from these 2 organizations, please drop us a line, let us know. And with that, thanks everyone for participating, and have a good day, have a good evening, wherever you are. Bye-bye.
Cheers.
Thanks a lot.
Thank you.
Bye-bye.
Bye. Thanks, Joe. Thanks, Nick.
Bye. Thank you.